Okay, so our next speaker this afternoon is Laura Schaposnik, who will speak about Higgs bundles, branes, and applications.
Thank you, Phil, for the introduction. Thank you to the organizers for the opportunity to speak at this great conference. I come more from the math side, so what I'm going to try to do today is entertain both you and me using slides, which I don't really use very often. So I've tried my best. I'm going to tell you about Higgs bundles and subspaces of the moduli space of Higgs bundles. Those are the branes that appear here. And along the way, I'll tell you about applications that these subspaces have and relations that they have both to physics and math. But I'm not going to go into any details of proofs or definitions. Those exist and are there in the paper, so you should take a look if you are interested. Instead, I'm going to try and give you the overview of where my work fits in and what are the inspirations that I get from. If you want a really, really short survey about the subject, it's that paper from March. It's only 3 pages, but most of the work is in several other papers that I've done either myself or together with my collaborators, David Baraglia, who's the postdoc in Adelaide, Australia, with Steve Bradlow from Urbana-Champaign, and with Nigel Hitchin from Oxford. So I'm going to start with the very beginning, what Higgs bundles. Yesterday you heard from Richard Thomas about Higgs bundles on projective surfaces. Today we're going to look at Higgs bundles on projective curves, so 1 dimension lower. Higgs bundles were first introduced by Nigel Hitchin, and I hope you don't get dizzy. So back in '87, Hitchin was studying self-duality equations in 4 dimensions, and he reduced these equations to 2 dimensions on a Riemann surface, and he got these equations that you see here that now we know as Hitchin equations. They're equations for a connection, and the solutions of these equations are what we now call Higgs bundles. So we're going to call sigma our compact Riemann surface, and K its canonical bundle. And on the Riemann surface, we can then define the solutions to those equations as Higgs bundles, pairs E phi, where E is a holomorphic vector bundle, and phi is a holomorphic section. That's our Higgs field. In the same way that we can extend the notion of vector bundle to principal bundle, we're going to extend the notion of Higgs bundle to principal Higgs bundle by taking a complex group. This has a formal definition, but since we're going to be taking today subgroups of the general linear group, all you have to remember is that when you take a subgroup of a linear group of GLN, you have to take classical Higgs bundles with some extra conditions that reflect the nature of your group. So for instance, if you were to take the special linear group, you're going to ask your vector bundle to have trivial determinant and your Higgs field to be traceless. For other groups, symplectic group, you'll put a symplectic form, etc. Once you put stability conditions, just like you saw yesterday, you can construct the moduli space of Higgs bundles, and that will be our main object of study. I'm going to call it MG, and I'm going to try to give you, before we start talking about my work, I want to tell you about 2 areas. There are many areas that are related to the moduli space of Higgs bundles, but I'm going to tell you 2 things that will be inspiring to ask questions about Higgs bundles. This moduli space, if you haven't seen it before, it's a quasi-projective scheme. It's smooth only under certain conditions, and it has a very rich geometric structure, some of which we're going to talk very soon. So the first inspiration that we need to bear in mind is its relation to the space of representations of the fundamental group of the Riemann surface. So when talking about unitary connections or representations, I think this year it's 50 years ago that Narsim and Ramanan gave us a theorem about that, and later on it's been generalized to Higgs bundles, vector bundles, and then Higgs bundles, and work of Yao and Uhlenbeck, and later on Simpson, Corlett, Hitchin, and Donaldson. So anytime that I give you a subspace of the moduli space of Higgs bundles, you can ask, what is the relation with representation theory? What is it telling us about representations? And I'm going to insist in this question because some of the subspaces that I'm going to hand to you will be related, in fact, to representation theory of 3 manifolds. And we're going to go back and forth between Riemann surfaces and 3 manifolds. The second thing that I want to keep in mind is the way of studying the moduli space of Higgs bundles, which is a way that Hitchin introduced in his second paper back in '87 in the subject, which now we call the Hitchin fibration, this map H. This is a fibration that makes the moduli space into an integrable system. The map H is a proper map into a very nice vector space, AGC. And what you should think about is taking a representative of your Higgs pair. So you take a Higgs pair, you send it to your characteristic polynomial that you see down there. the characteristic polynomial defines for you the spectral curve that we're going to call S. And over this spectral curve, which is generically smooth, irreducible, over that you have an abelian variety, a compact abelian variety, which will be either a Jacobian for these complex groups or a sub-abelian variety of your Jacobian. So it's a very nice and neat way of seeing a moduli space that was in principle quite complicated as abelian varieties. This is what we call abelianization of the moduli space. And since we can do this for groups, for complex groups, we can take other types of groups, which we've heard a lot about during this week, which are Langland's dual groups. If you haven't seen Langland's dual groups before, I put some here for you to keep in mind. These are the ones that we're going to be using. And what happens is that if you take Higgs bundles for the Langland's dual group, it fibers over a base which is isomorphic to your original one. So suddenly you have two moduli spaces which fiber over the same base, and it was conjectured by Zaslow, Strominger, and Yao that the duality should be seen as the duality of toric abelian varieties. So among other things, that homological mirror symmetry should give you a correspondence between compact abelian varieties that are dual to each other. There's much more behind it, but this is one of the features that we're going to keep in mind. So let's see an example. If you took classical Higgs bundles, so GL and C Higgs bundles, your fibers are Jacobian varieties, which are self-dual, and your general linear group is self-dual too. If you took SL and C, this was first proven by Hausel and Thaddeus back in 2002. This was the first case that was seen. And what you get is, in one side, the prime variety, the kernel of a nice map, the norm map, and in the other side, the dual abelian variety. So, as I was saying, in 2002, Hausel and Thaddeus saw the first case of this duality appearing in the Hitching fibration, and later on, Donaghy and Pantev, and Kapustin and Wheaton, and Hitching, and many others have generalized it in a much more broader setting. So we're going to keep these two things in mind. We're going to keep the Hitching fibration with Langland's duality or mirror symmetry telling us a duality between fibrations, and we're going to keep the relation with representation theory in mind. And anytime I had a subspace of the moduli space of Higgs bundles, we're going to ask questions in those directions. Now we're going to focus with one particular geometric property that the moduli space of Higgs bundles has, which is a Hyperkahler structure. This means there's a family of complex structures, and there's a family of compatible symplectic forms that give structure to the moduli space. I'm going to fix three of them. I'm going to call them I, J, and K. These satisfy the quaternionic equations. And I'm going to call omega I, omega J, and omega K the corresponding symplectic forms. The way that I'm going to fix them is in accordance, for instance, with Kapustin-Wheaton and with Hitching, where I call I the complex structure coming from the Riemann surface, and J the complex structure coming from the complex group. So one of the ways that you can think about this is by taking the underlying manifold, the smooth underlying manifold of your moduli space, and thinking that if you put complex structure I, you recover the moduli space of Higgs bundles. But if instead you put the complex structure J, you recover the moduli space of flat connections or representations. So having three complex structures fixed and three symplectic forms, now anytime I give you a subspace of the moduli space of Higgs bundles, you can ask, is it a complex submanifold with respect to one of those structures? Is it a Lagrangian subspace if it's mid-dimensional with respect to one of the symplectic forms? And you can ask these with respect to any of the structures that I've given you. So we're going to now adopt the physicist language, roughly speaking, and talk about branes. We're going to say that a holomorphic submanifold with a holomorphic vector bundle is a B-brane, and that a Lagrangian subspace together with a flat connection is an A-brane. Now, this is roughly speaking. There are more branes than the ones that I'm taking here, so that's why this is not a definition. We're just taking in this direction the statements. We are going to be asking questions about subspaces of the moduli space branes inside the moduli space of Higgs bundles. But the first question that one needs to ask when talking about branes, as you see on the screen, is what is the base? So once we understand the base, we can understand then the holomorphic bundle or the flat connection. So from now on, I'm going to ask the first question, what is the base? And I'm going to talk about branes as just the base. And if you haven't seen this notation before, my trick is to know that Lagrangian is with A. And that's going to be your A-brane. So we can ask this question about the three structures, the three complex structures, and the three symplectic forms. And a natural question to ask then is, how can we construct branes of all possible types? If you do the linear algebra to see which types of branes can you have in the moduli space of Higgs bundles, you'll see that if you wanted to have an AAA brane, so something that's Lagrangian with respect to everyone, your symplectic forms would have to be degenerate, and that can't happen. So these are the four types of branes. So BAA, for instance, means that it's a complex submanifold with respect to I, but it's Lagrangian with respect to omega j and omega k. A BBB is a hyperholomorphic brane, which is a Hyperkahler subspace of your moduli space supporting a hyperholomorphic sheaf on top of it. For instance, the point or the whole space. And the first Lagrangian subspace that was one of the first spaces that was studied was back in '92 when Hitchin was looking at Tech-Muller space inside the moduli space of Higgs bundles. What he saw is that this space was actually given by Higgs bundles for a real form. And if you take, so I'm going to take a real form of my complex group, and a real form G is a subgroup which is fixed by an anti-holomorphic involution. So we're going to call sigma an anti-holomorphic involution of the complex group. And we're going to call rho the compact involution, so the one fixing the maximal compact subgroup. If then you define the involution that sends a pair E phi to sigma rho E and minus sigma rho phi, what you're doing is you're asking the holonomy of that connection, that was the solution of Hitchin's equations, to have holonomy inside G, the group, the real group G. I've set there some examples for you to have. Those fixed points, the fixed points of this involution give a Lagrangian subspace, which is in fact a BAA brane. So it's Lagrangian with respect to omega j and omega k, but it's a complex submanifold with respect to I. So we want to be able to construct examples of branes inside the moduli space of Higgs bundles of the other types. And since this is a quite neat way of constructing one type, with my collaborator David Baraglia, we thought of trying to construct the other ones in a similar fashion. We've taken a complex group, and we've taken a real structure on the group, but we also have a complex manifold. And so we can take a real structure on that manifold. That's what I called F there. So F is a real structure on the manifold. So locally, Z goes to Z conjugate. And through this real structure, you may define a second involution. So it's the one that I called I2, which sends E phi to F rho E and minus F rho phi. What's doing is it's an involution, it's a holomorphic involution in your moduli space, and the fixed point set of this involution give you an ABA brane. And if you compose these two involutions together, that gives you an AAB brane. So we constructed examples of the three of the types of branes using real structures both on the group and on the Riemann surface. And what I'll do in the coming minutes is tell you a bit more about how these branes appear in the Hitchin fibration, what's the relation with representation theory, etc. I'll try to, along the talk, tell you what the results that I'm giving you are useful for, that I'm aware of some of them, or how have they been generalized. And for what I know, I think that these constructions have been generalized for framed instantons and quiver varieties, among other things. So we mentioned that there was Langland's duality telling us a duality between Hitchin fibrations, and we can take the first brane BAA and ask what happens with branes in this duality. So Kapustin and Witten have proposed that the duality should also be a duality of derived categories, which means for us it's a duality between branes inside the moduli spaces. And from the physics perspective, we know that from their paper, the BAA branes should have a dual BBB brane, so a hyperholomorphic brane inside the moduli space of dual Higgs bundles. If we take then the BAA brane coming from real Higgs bundles, so connections whose holonomy is in a real group, we should ask what is this dual BBB? And the proposal that we have with David Baraglia is that the dual brane should be the space of Higgs bundles for the complex group, which is Nadler's group. David Nadler was studying loop Grassmannians, and he constructed a complex group inside the Langland's dual group associated to each real form. I set there some examples. If you look at Higgs bundles for that complex group, from the way that this brane lies inside the Hitchin fibration and the properties that it has, it really looks like it should be the case. There's some further support from Nigel Hitchin for one group, and his current student, Lucas Branco, should have in his thesis some nice support for the conjecture for those groups there. And hopefully, I think Gayotto tomorrow will tell us something about these from the physics perspective in some low-rank cases. And we're hoping to have a much more deeper physics intuition in terms of branes for this conjecture. But we can also ask, how does this brane lie inside the Hitching vibration just itself, within the regular fibers of the Hitching vibration? And there are two cases that I want to focus on, which are when this brane intersects the generic fibers in an abelian way, and when this brane intersects the fibers in a non-abelian way. Since we started with an abelianization of our moduli space, it's interesting to see the two cases. The first case, the abelian intersection, happens in several situations, but one that I could see is that if you take G, your real group, to be the split real form, so for instance SL and R with respect to SL and C, what happens is that the intersection of this brane with the Hitching vibration is on points of order 2, so 2 torsion points in each fiber. This means you have the Hitching base, and over that you have a finite covering given by these torsion 2 points. And then you could, for instance, study the Gauss-Manning connection, the holonomy, to get information about your brane. The connectivity will depend, for instance, on the orbits of this Gauss-Manning connection. You can also calculate characteristic classes depending on where these points lie. So this is one of the situations where, and you'll see in the last slides how we use this with Steve Radler for another setting studying Higgs bundles. The other case is non-abelian intersection, and this will be, in fact, the most common scenario. And what happens is, for instance, in these three cases, what we could see with Nigel Hitching is that if you take the special linear group with the quaternions or the subgroups of that group, which are SO to an H, or the split symplectic group, when you look at the brane intersecting the generic fibers of your Hitching vibration, it doesn't intersect. So the generic fibers in that vibration are not intersected. The brane lies completely over the singular loci of your Hitching base. And if you look at the intersection with that singular fiber, what you'll get is some subspace of the moduli space of rank 2 semi-stable bundles with fixed determinant. So it's a non-abelian, it's what we call the non-abelianization of these branes, because it's non-abelian space intersecting the singular fibers. And this has proven to be quite useful when studying the dual BBB brane by Lucas Branco. So these are the ways that it intersects this BAA brane of real Higgs bundles, the Hitching vibration, but there were other branes. There was an ABA brane that we constructed using a real structure on the complex surface. And we can ask the same question: how does this brane intersect the generic fibers of the Hitching vibration? This is in fact quite nice, and what happens is that you have your real structure F acting on your Riemann surface. The fixed points are circles, and the invariants of these F are the number of circles and the way that they are laid on the Riemann surface. Depending on that, you get the geometry and topology of your brane. And what we could prove with David Baraglia is that you actually get a real integrable system fibering over the real loci of your Hitching base. So what you get is a singular Lagrangian fibration where the generic fibers are a collection of tori, the number of which depends on the invariance of your involution F. So, for instance, we haven't found more applications of this real integrable system. But we can go further and ask, what's the relation with representation theory? What is happening in the case of representation theory is not going to be really so much in relation with representations of the Riemann surface, but with representations of three manifolds which bound the Riemann surface. So what we could see is that if you take a Riemann surface whose boundary is, if you take a three-manifold whose boundary is the Riemann surface, and you ask which connections extend from your boundary to your three-manifold, the same way you would ask if you had a knot or a graph inside S3, and you look at the complement and you ask that question. And the answer is, if you take a three-manifold and you're able to express it as it says there, as a product of the Riemann surface with an interval and a quotient by the involution, that three-manifold has as boundary your Riemann surface. And when you ask that question, we can tell you which representations extend. Those are the ones in the ABA brane whose K-theoretic class is trivial. This class of the vector bundle is, roughly speaking, created by the action of the involution that we had on the fixed point set on the Riemann surface and on the bundle itself. So there's a very naturally defined K-theoretic class that vanishes. And there are some directions in which one could try to carry forward these ideas, because as I was saying, if you have a knot or a graph inside S3 and you ask the question in the complement, what things extend, what representations or connections extend from the boundary to the three-manifold, that's what the A polynomial or generalized A polynomial is giving you. So somehow these branes should have to do with those polynomials. And if you took, for instance, a three-manifold without boundary and you a compact three-manifold and you looked at a Heger decomposition, your Casson invariants should appear in terms of intersection of branes, if you could write them in this way. And we have the intersection of the brane with the Hitching vibration, and we had the relation with representation theory, but we can also ask again, what happens with the dual side? What happens with Langland's duality and what Kapustin and Witten told us about dual branes? They've told us that ABA branes are of self-dual type, so there should be an ABA brane in the dual moduli space, giving us representations that extend to the dual group. So the proposal with David Baraglia is that the dual brane should be what you really probably expect, is you're taking the same Riemann surface, so you may take the same real structure F, but instead of taking your compact form in your group, you take the dual compact form. And from the way that this brane appears and the geometry that it has, it would seem that this really should be the dual brane. So I want to finish the last minute or couple of minutes with some further questions that I've been thinking about in the last month or year, which is, since we're very interested in understanding Langland's duality and mirror symmetry in terms of vibrations and relations between branes, what other moduli spaces can I put that would fiber over the same base or isomorphic basis? And is there, if so, any relation between branes, and can I construct relations which give us correspondences between branes of the same type? Many times from a physics perspective, you're interested in knowing corresponding branes of the same type in moduli spaces. So we've started tackling this question with Steve Bradler by considering different types of representations, like symmetric, antisymmetric representations, or considering products of groups, like the GC, cross GC, or cross GC, etc. So I'll show you one example of how this works. It works in much more generality, but this has many details that you should take a look in the paper. But this is the idea. You start, for instance, with SL4C, and you look how can you create a correspondence with the orthogonal moduli space. And the way that you do is you go through a middle point of looking at products of moduli spaces, and then you get naturally the orthogonal moduli space. And the way, in terms of the Hitching vibration, that this procedure works is by starting with your spectral curve, corresponding to a special linear group Higgs bundle, and you take a fiber product. It's always through fiber products that we're able to develop this correspondence. You have to quotient by a natural involution that appears. You have to then take the diagonal from inside and symmetrize, but at the end of the day, what you get is the naturally smooth spectral curve of the orthogonal group. We've been looking at the correlation then of real forms. If you take this procedure and you ask what happens with our BAA branes coming from real groups, if you look at the split real forms, we get indeed a correspondence between BAA branes, and in fact it's a covering, it's a 2 to a 2G covering of BAA branes, where the covering depends on the Stiefel-Whitney classes of your Higgs bundles. So there's some relation with the topological classes of the Higgs pairs. And what's been this useful for, in particular with also joined with John Loftin and Ian McIntosh and Steve Bradler, we are trying to, we're parametrizing minimal surfaces using spectral data by starting with low rank things and getting to higher rank by doing this procedure. So this is all I wanted to tell you. Thank you very much.
Are there any questions?
So can I ask you some naive questions? So
yeah.
If you have purely B branes like BBB,
yeah.
I think that's easy to see what's the sheaf theoretic object that corresponds to that.
If you have BBB branes?
Yeah.
Which BBB branes?
I guess as long as you just have holomorphic structure, then you can come up with a sheaf theoretic a sheaf that corresponds to that brane. As long as you have
Yes.
only purely a brane structure, you can also come up with some kind of sheaves or complexes of sheaves.
So for the BBB branes, Hitchin had a proposal using determinant line bundles, hyperholomorphic shapes that he constructed. But this is a proposal. All these conjectures are, it's not even clear how one would prove these conjectures, right?
So do you know what is for example, BAA brane mean, sheaf, as a sheaf? What's the sheaf?
What's the sheaf that should be supported on the BAA brane? I would know. I would guess, but better not.
I'm trying to understand when you say.
So I'm thinking. Remember, I'm thinking of the support of the brane.
Yes, yes.
Right.
I know.
So I'm thinking of the Lagrangian subspace.
I understand.
And then I'm hoping to take, for instance, for the BAA, say coming from split real forms. We said for split real forms you have a finite covering of your Hitchin base, so it's just points in each fiber. So that's our BAA brane in one side. If you take like the trivial sheaf support on each of these points, that will give you a hyperholomorphic brane in the other side, which is supported on the full moduli space. The rank of the hyperholomorphic bundle will depend on the number of points that you had in one fibration. I mean, I'm speculating.
So the reason I'm asking you this question is that in geometric Lagrange dualities and so on, I mean, the ones I thought I understood. I mean, some of them, they have these Fourier-Mukai transforms.
Yes, that should exactly be the way of getting them. Taking the sheaf, so once we understand the support, taking a sheaf in one side and trying to do Fourier-Mukai to get these.
So this also, you can do it with these ones?
Yes.
Okay.
Yes.
Are there any other questions? If not, then perhaps we'll thank Laura again for her nice talk.
Thank you.